In this lesson, we're going to prove certain derivative formulas for exponential functions. But before we begin, we should introduce you to the constant e. E is an irrational number that's approximately equal to 2.718. Think of a number like pi, which is approximately equal to 3.14. It's an irrational number, meaning it goes on forever with no repeating, but we all sort of accept that that's what pi is. Well, maybe a little bit less known, but very important to mathematicians, is the letter e, is the constant e. And by definition, e is equal to the limit as n goes to 0 of 1 plus n quantity to the 1 over n. So to show you what we mean, we'll let n go to 0. So let's let n equal 1. 1 plus 1 to the 1 over 1 is 2. Now let's let n go to 0, so let's let it be 0.1. Well, 1 over 0.1 will be 10. So 1 plus 0.1 to the 10 is approximately 2.594. Let's let n now get closer to 0. We'll let it be 0.01. 1 over 0.01 is 100. 1.01 to the exponent 100 is approximately 2.705. Well, if we keep letting n be smaller and smaller, we'll eventually see that the limit as n gets closer to 0 of 1 plus n to the exponent 1 over n will end up equaling e, where e is approximately 2.718. We should also talk about something called the natural logarithm of a function. And the natural logarithm is the log base e, where e is this accepted number. And we often say natural logarithm, or we often call it ln. So the ln of x is the log base e of x. Now, the first formula we're going to talk about is we're going to prove that the derivative of ln x with respect to x is 1 over x. Okay? So how are we going to do that? Well, we'll start with the definition of derivative. The derivative of f of x with respect to x is the limit as h goes to 0 of f at x plus h minus f at x over h. So we just use ln x in terms in the place of f at x. Now, it's a property of logarithms that the difference between two logs is equal to the log of the quotient, as long as the base of the logs is the same, and that's what we have here. So we can re-express that numerator this way. We still have a denominator of h. And we can break apart this fraction. X over x plus h over x is definitely equal to x plus h over x, so we can break apart that fraction this way. Now, x over x is clearly equal to 1, so we can pull that out, and we still have h over x here. Now, what we're going to do next, instead of having a numerator and denominator, we'll pull that denominator out. We'll say 1 over h times the ln of the numerator. That's just actually simple fraction work. We can just kind of pull that denominator out, call it 1 over h. Then, another property of logarithms that you may recall is that a log b is the same as the log of b to the a. In other words, we can take this right here and move it up into the exponent place. Okay. Now, you'll recall what we have at the bottom is the ln of 1 plus h over x to the 1 over h. Well, what we're going to do now is just multiply this exponent by 1, but we'll call the 1 x over x. Okay, so now we have an exponent of 1 over h times x over x. We'll just change that to to x over h times 1 over x. So x over h times 1 over x will give us the same result. Now, this is again in the position of the exponent, so we can actually bring that down here using the laws of logarithms. Okay? Now, we end up here, hopefully you understand that, and then we do something kind of nifty. H is going to 0. So, since h is getting infinitely small, h over x is getting infinitely small. So instead of saying h is getting to 0, we say h over x is getting to 0, which is clearly true. And we still have 1 over x ln of 1 plus h over x to the x over h. Now, it's a property of these types of situations. You might not have known this, but we can, instead of saying the limit of 1 over x times the ln of this, we can say 1 over x times the ln of the limit of this. So we're just sort of rearranging these three introductory pieces there, and that's a property of limits. It's legitimate. Now, what we're going to do next, this is kind of neat, we're going to let w equal h over x. So that'll be a w right there, and that'll be a w. Well, if w is h over x, then 1 over w will be x over h. So that will be a 1 over w. And so what we'll have is 1 over x times the ln of the limit as w goes to 0 of 1 plus w to the 1 over w. Well, what is this? You might recall from the previous page, we said the limit as n goes to 0 of 1 plus n to the 1 over n is e. So the limit as w goes to 0 of 1 plus w to the 1 over w is e. Now, we're doing the ln of e. Well, that's like saying the log base e of e. Well, e to what exponent gives us e? The answer is clearly 1. So the ln of e is 1. So we have 1 over x times 1, which is 1 over x. And that's what we were trying to prove, that the derivative of ln x is 1 over x. Okay, now let's move to the next proof here. We want to prove that the derivative of e to the x with respect to x is e to the x. It's a pretty neat property of the function e to the x, that every y-coordinate is the slope of the tangent line. In other words, the derivative is itself. Well, let's prove that. Let's start with y equals e to the x. Now we can take the ln of both sides. That's a legitimate thing to do. Do the same thing to both sides. Now it's a property of logarithms that we can bring that x in front. So we can say the ln of y is equal to x ln e. Well, we know that the ln of e is 1. We discussed that a minute ago. So we're saying that the ln of y is x. And now we're going to do implicit differentiation. If the derivative of ln x is 1 over x, then the derivative of ln block is 1 over block times the derivative of the block. In other words, the derivative of ln y, using implicit differentiation, is 1 over y times dy dx. The derivative of x is 1. We multiply both sides by y, and we get dy over dx is equal to y. Well, remember that y is equal to e to the x, so we can say the derivative of e to the x with respect to x is e to the x. Okay, and now our third proof is this beauty right here. We're required to prove that the derivative of b to the x with respect to x is b to the x ln b. Now, to do this, we're just going to try and recall that it's a property of logarithms. W to the log base w of z is equal to z. That's a property of logarithms. Now, if we let w be e and we let z be b to the x, then we can rewrite this statement as b to the x, z, b to the x, is equal to e log base e of b to the x. Log base e is ln. So we can say b to the x is equal to e to the ln of b to the x. So let's now prove this. We're going to let y equal b to the x. So that's like saying y is e ln b to the x. So in other words, we're letting y be b to the x, and we're going to figure out its derivative. Well, to say y is b to the x is like saying y is e to the ln of b to the x. Now, what we can do here next is we can take this x right there and just bring it in front of that ln. We call it e to the x ln b. Now, what we're going to do is take the derivative of both sides. Well, this is just y equals e to the x ln b. Imagine just for a second if ln b was a number that we're familiar with. Let's say 7. Let's say y is equal to e to the 7x. Well, if y was equal to e to the 7x, then we'd say the derivative is e to the block times derivative of the block using a chain rule. So if y was e to the 7x, we'd say y prime is e to the 7x times 7. So this is no different. y prime is e to the x ln b, just leave it alone, multiplied by the derivative of x ln b, which is clearly ln b. So again, that takes a little getting used to, but just for a second, imagine the ln of b is something like 7. That'd be like saying e to the 7x, the derivative is e to the 7x times 7. So if we're saying e to the x ln b, then the derivative would be e to the x ln b times the ln of b. So we can now take this x, put it back up here, and we get e to the ln of b to the x times ln of b. And based on this whole conversation we had here, e to the ln of b to the x is the same as b to the x. So we can substitute that in, and we have y prime is b to the x ln b. So in other words, the derivative of b to the x with respect to x is b to the x ln b.